Hello, everyone. Welcome back. So can you hear me? Okay. And I hope you can see me as well. Okay, great. So thanks, everyone, for joining. Both those that are returning after previous talks, and also those who are joining for the first time. Those who came from previous talks may notice that this is a different room. Still in the same house, we're still being quarantined here in Israel for a while. So I haven't been going out much, but I found a different location in the house where I think the setting is a bit nicer. Okay, so today's topic is going to be, it's actually a topic of considerable, can you see this screen now, Sheridan? Can you, okay, I guess you can, right? Okay. Just making sure, can you guys see the screen? Okay, yes, great. So today's topic is something that actually is a very deep topic in math and complexity, and it is. Let me just make sure that I have the right size of pen here, and it is soundness, which, and I use this teaser in sort of a local epistemology. So epistemology, so I'm told or read on Wikipedia, is a subject in philosophy that talks about, what is knowledge and what do we know about others' knowledge and what can we know. So soundness is some mathematical version of epistemology in which we sort of make succinct or local examinations of something, and we're trying to deduce from it a whole lot of stuff about what goes on in the head of some other entity, the prover in this case. So basically the setting, and I want to, again, as usual, for those who haven't attended previous webinars, I'm not going to prove any theorems here or define anything very formally. I will maybe send an email afterwards with all kinds of pointers where you can read about stuff. So the main goal in these things is to give intuition and some sort of idea of what goes on when we discuss these mathematical notions, so that if you encounter them or if you study them and read them, you'll have some sort of insight, I hope. And then, of course, you need to sort of work out whatever your understanding is. So the setting is, and this is very typical, this was the starting point for almost all the talks that I gave here. Will continue to be, just to make it concrete. Suppose that a prover comes along, and again, I'm taking just an example that's very close to what we're doing at Starkware, so it's very easy for me to describe, and it's also very concrete. So the prover comes along and says, I processed, let's say, 10K transactions. They're all good. So, let's move the state of the account database in some system that, let's say, holds payments or accounts on behalf of users from some Merkle root, some Merkle root A, which was the previous, to some new state Merkle root B, based on those transactions. And now this is this is the statement that the prover makes. And now there's some interaction going on. So there's this interaction where basically there's a statement sent, there's some string sent to the verifier. I mean, there's a verifier here at the other side. And there's interaction back and forth. And at the very end, right, so there's some sort of transcript that arises here. Transcript. Tau, and this tau depends on random coin tosses of the verifier, and maybe on random coin tosses of the prover. So there's this protocol, this transcript, And at the very end, the verifier sort of thinks about it and then says, you know what, I accept. Meaning, based on what I've seen, this is convincing according to the protocol that I expected, and I'm going to accept this, and let's move the state from the Merkle root A to the Merkle root B. And the main question, this sort of epistemological question that we have is this wise? Is this wise on behalf of the verifier to do this? To accept this, we would like to accept it if we get some sort of good feeling about the prover actually knowing and seeing these transactions and processing them correctly. So basically, what if prover cheats, right? And in everything we're doing, we're looking at things that are very succinct. So the amount of information that passes by here between the prover and verifier is very limited in its size, and it's much, much less smaller than the amount of information that describes these 10,000 transactions. And the amount of computation that the verifier is doing is actually logarithmic in the time it would take to verify all of these, signatures and amounts and order limits and everything that needs to be checked. So we really need to get some good assurance that we're accepting something only when the prover has done something okay. So that's where soundness comes in. And soundness theorems typically, they have some sort of structure that looks like this. So all soundness theorems that in the interactive proof setting, they look something like this. They say if the probability over these random transcripts that the verifier accepts with this transcript, right? So it accepts the statement given the transcript. If this probability is greater than some epsilon, then something good happened. Then we would like to say statement is valid. That's one kind of epistemological, conclusion that we would like to reach. And often there's something called knowledge soundness, which is even something stronger. Moreover, we'd like to say the prover actually knows, and this is where things get even more interesting and philosophical, knows a witness proving statement. So, for instance, in the case of the statement above, what such a theorem would its conclusion would be that the prover actually holds somewhere in her head information about all of these 10,000 transactions, and all of this information would pan out nicely. So again, soundness theorems, and there are many of them in the literature that have been proved, and we're constantly working on improving other ones with better parameters, and I'll explain what are the parameters that matter here. All of them have this flavor. They say if the probability over the random choices of the verifier and the prover, if the probability of the verifier accepting basing on the fact that it saw this transcript tau, if this probability is greater than some number epsilon, then this was okay, because then the statement is valid and the prover knows some witness that proves the statement. And we'll get to the discussion of what it means knows. So now let's just pause to appreciate this theorem. If we now go back to the original setting and we see a verifier, and we invoke this verifier, and the verifier, did some interaction and then accepted a statement. What such a soundness theorem tells us is that there is some probability that this was a mistake to accept it, meaning that actually the prover got away and he doesn't know this thing, or maybe he knows something else. Maybe the statement just is impossible and can't be true. But that's very unlikely to have happened, right? Because the probability that this would have happened is extremely, that the prover is dishonest or lying, or the statement is wrong, or he doesn't know the witness. The probability that that is what happened is very small. It's smaller than epsilon. And you can think of epsilon, epsilon is typically, let's say, you can set it to whatever you want, but we could take it to be something like 2 to the minus 100 or something like that, or 2 to the minus 128. Good. So this is what soundness analysis is about. It's about once you specified your protocol, you would like to prove that if some tiny little bit of amount of transcripts, like a tiny fraction of the transcripts is accepted, then actually there's something global that you can deduce from this. Because each transcript is extremely small and short. Okay, I want to, I usually go back and ask if people have questions. So that's what I'm going to do right now, and we'll continue. Any questions so far? So please use the questions. I see there's already one, and I encourage you to type questions as you see. So Aline is asking, isn't this variant of soundness actually called knowledge soundness? I thought it was possible to define soundness to say only the statement is valid given the witness as input to the prover and verifier. So Aline, you are indeed correct. I was mixing soundness and knowledge soundness. So just to clarify to everyone, usually soundness refers to a task that asks, is the statement correct or false, right? And then a soundness theorem would say, well, if the verifier accepts with probability greater than epsilon, then actually the statement is correct. Okay? That's one kind of soundness. There is another kind of soundness, as Aline is pointing out very correctly, which is knowledge soundness, which says a lot more. It says that if the verifier accepts, not only is the statement correct, but there is a procedure, there is some efficient and effective way to sort of extract the witness from the prover in a very concrete sense. Okay. So the next question is, what is the probability space? Very good question. Dimitri is asking. So the probability space is the probability space defined by the random choices of both the verifier and the prover, but we sort of quantify over all malicious provers in the world. We would like to say no matter what the prover does, and it can be also a probabilistic prover, so it can use randomness as well. Based on the randomness, both of the verifier and the prover, for any prover, if you accept it with probability greater than epsilon, then the statement is correct. And in the case of knowledge soundness, not only is the statement correct, there is a procedure to extract a witness from that prover that convinced you that the statement is correct. Okay, great. So I want to go back. Let me go back to the screen. And now, so I want to argue very informally what is really going on here. Let me just use some other colors. So there's, as Dimitri was pointing out, there's this big, there's this big probability space. There's some probability space of all possible transcripts, right? These are all possible transcripts. And what do we know? Well, we know that there's some tiny fraction that's good. It's at least epsilon. And it can be arbitrary, and then everything else is bad. Those are the bad transcripts, right? And basically what we need to do is, given any set of transcripts, taus, I mean, it just has to be large enough. That's an epsilon fraction of the space. There's some way to extract from it, there's some way to decode decrypt or whatever it is, a witness, or a witness for the validity of the statement. So really what's going on here is that, and that's the sort of the task that we need to solve. We need to, we first define a protocol, and then we need to argue, and that's where it gets very hard, that no matter which fraction of transcripts we are given, that is sufficiently large, it's an epsilon fraction of transcripts, it somehow contains within it enough structure to extract from it or decode from it or construct from it enough information that would just show us that the statement is valid. In the case of the statement I described, you need to take these good transcripts and from them construct the actual, let's say, 10,000 transactions and the updates to the database and the Merkle paths and everything that would lead you to move from state Merkle root A to Merkle root B. That's what you need to do based on this set of this fraction of good things. And I just want to mention that this task, so soundness analysis, gets harder as epsilon shrinks. And you can, from this picture, you can already intuitively guess why this is the case. If like 99, if the green region is like almost everything, then it means that there's a lot of good structure and a lot of good things happens. And then you have sort of a lot of information in your hand from which you can sort of construct the witness that you're looking for. But as you make epsilon smaller and smaller, it becomes harder because you have fewer good, starting points to sort of glue together and reconstruct the witness. So it gets harder as epsilon shrinks, but you definitely want to shrink epsilon as much as you can. So as much as you can, because this would mean this will imply that your protocol gets more efficient. As epsilon becomes smaller and smaller, it basically says that the probability of error of accepting something that you shouldn't accept becomes smaller. So you want to shrink epsilon, but it makes the problem harder, and that's where the challenge and beauty of soundness analysis arises from. Okay. So going back to this sort of epistemological notion, everything that we do in soundness analysis is construct protocols, and they better be simple enough that we can sort of look at the transcripts and say, okay, these are the portions of this transcript that we're going to use in our construction process. And then we need to work really, really hard and take those parts of the process and glue them together and find from them, sort of clean all of the bad stuff and say, oh, look, there's some diamond in the rough here. There's something here that tells us that everything's okay. And that's where things get really challenging and interesting. Okay, so I'm just going to pause here and ask once again, or just see if there are any questions about this. Good. Does there exist, so Mikhail is asking, does there exist some protocol which is sound but not knowledge sound besides the trivial languages? So I don't recall off the top of my head. I am guessing that you could probably at least construct such things. I want to say that at the very least, in all of the protocols that I ever got to analyze, there were different epsilons for or different error rates for soundness and knowledge soundness. For knowledge soundness, you need more structure, and I'll explain why. For plain soundness, you just need to say, well, there's some witness that can be constructed from the good, the green part. Maybe the way to construct this witness is extremely inefficient, like maybe I need to enumerate overall, an exponentially large space. That's still okay. To prove knowledge soundness, you need to have enough structure that you can show that there is an efficient polynomial time procedure that, given the green stuff, can reconstruct efficiently the witness. So typically, even when there's soundness and knowledge soundness error is bigger. It requires a larger set epsilon because you need to do something constructive. Okay, very good questions, thanks. So, okay, next question. If you're not participating in a system as a prover or a verifier, but as an observer, so to speak, is there a concept of soundness there, or solely assumptions on the validity of the system? That's a terrific question, and I'm trying to think if I'm even qualified to answer it. So it gets very philosophical. Like, for instance, systems like Stark's, they're transparent, which means that the verifier is, all it needs to do in the interaction is supply public random coins. So now suppose you're observing from the side this process. Well, you have to worry. I mean, the question is, do you trust that the verifier is actually providing, honest randomness? Or is this randomness really sampled independently? Because otherwise the verifier could collude with the prover and offer unfair randomness. So it's really about, as an observer, what are your assumptions on the process you're viewing? So I'll give some examples. One example is that suppose that the prover submits something to a blockchain and as its message, and then since all we need is public randomness, it takes this randomness from the next block header. So, even there, it's a question of belief, or also one could do some cryptoeconomic analysis here, because maybe if the statement being proved now involves something that is worth $1 million, so maybe doing a reorg on some blockchain like Ethereum or something like that would cost less than that, let's say 100K, and you're observing this process. I don't know, maybe the verifier, this public randomness was actually massaged by the prover. A different option, but again, it's one of the sort of assumption or belief, is to use what's called the Fiat-Shamir heuristic, and to say, well, we make the system, for all practical purposes, deterministic, meaning that whenever there is a message from the prover, the verifier's randomness is something like, the hash of the latest prover message, which is sent to, let's say, SHA-2, and you get the randomness from that. So you're treating something like SHA-2 as a purely random oracle. Again, that's an assumption or a belief, but and then if you assume that's if you assume the Fiat-Shamir heuristic, then again you should trust it even as an observer. And same thing, if you trust the randomness coming from the blockchain to be good, then you should. Great question, thanks, Karen. Okay, next question. Isn't there somewhat a contradiction between the proof being succinct and much, much smaller than the witness to the existence of a knowledge extractor for a witness? If there is not enough information in the transcript, you cannot extract a big enough witness. So in the example of massive verification of the blockchain, what is the witness? Excellent question, Yaakov. Excellent, right to the point. So let's see. Yaakov is saying, of course, the amount of interaction is extremely small. How can you hope to extract a witness from this small amount of information, right? It could be, as small as, let's say, a few kilobytes or a few bytes. How can you extract from that any information about something that involves 10,000 transactions? So the answer to this is that our assumption was not about one particular transcript. Our assumption was that we have an epsilon fraction of transcripts. Each one of these transcripts is very short, but an epsilon fraction comes typically from a huge space. So if you count the number of, let's say, bits of information in an epsilon fraction of transcripts, that typically is much, much bigger than the amount of information in the witness. And indeed, that's exactly how the soundness analysis works. Each one of the interactions or transcripts is very short, but you have a whole bunch of them. It's not such a large fraction. It's epsilon. It could be something very small, and it's very arbitrary. You only know it's an epsilon fraction, but that's what you work with. So that's the answer. And again, going back to this image that I use of pointillism and sort of having a global structure emerging from many small points, that's exactly the process that the soundness analysis mathematician has to confront, to take these small transcripts and glue them together and get this global picture, which is the witness. Okay, next question. Terrific questions. Thanks, everyone. Isn't the Fiat-Shamir heuristic unsecure in the random oracle model? I don't want to go into this question for two reasons. First of all, I am not an expert on Fiat-Shamir. Okay, so like I don't want to go there, and I think Fiat-Shamir heuristic sort of says, well, let's just assume that, the random oracle model just cannot exist mathematically and physically. So, but it's a very convenient model to analyze. So that I think my interpretation or understanding of the Fiat-Shamir heuristic is to say, well, even though SHA-2, for example, is very far away from a random oracle, let's just assume that everyone who uses it treats it as a random oracle and that everything works fine, something like that. Okay, next question. And this will be the last one I'll answer because I want to go back. So for a given size for witness, the smaller the epsilon, the larger the number of transcripts. Let's see. So for a given size of the witness, the smaller the epsilon, the smaller the epsilon, the smaller the number of transcripts. The way we do, we work with it. Let's say, when we analyze things like Stark or Fry. There's a basic protocol. You have a fraction of transcripts. And then shrinking the epsilon means that you look at the same protocol, it's the same set of transcripts, but you can reconstruct witnesses even with less and less fraction of them. So that's the problem. And then it becomes more challenging, but if you can do it, you get better protocols. Okay, terrific questions. Let's go back and continue. So now I just want to mention, because, Starks and these, Starks is, of course, just one out of a large family of protocols. I'll mention a few of them because they're all sort of very similar in being information theoretic. So I want to put here, let me just pick a different color now, oops, actually want to be line. Oh, I wanted a line. Good. So now here, suppose we have things like, let's call them transparent protocols. Things like, so there's things like Ligero and Zikaboo and Stark, and there's Aurora and Fractal and a bunch of others. These are not the only ones, but they're all similar, and they're the kind in which you do soundness analysis. And on the other hand, I want to put here the ones for which you do typically security analysis. These are things like, snarks, like Groth 16, things like Plonk, Slonk, Bulletproofs, and there are many, many others. And I want to just emphasize the difference in the analysis. So here we have information. So here we do soundness analysis. So here we have information theoretic, sort of mathematical proofs that reconstruct witness from small fraction of good transcripts, of accepted, right, transcripts. That's what we have on this side. On this side, usually we have some crypto assumption that looks typically something like this. The only way prover could reach this transcript is via this method, which we think of as the method that should be safe for us to use or assume. Like the only way these things are, they're seeing things like knowledge of exponent assumptions and groups of unknown order assumptions and things like algebraic group, unknown group assumptions, and all of them have a similar flavor. They look at some part of the protocol that's very essential, and they say, okay, well, one way to do it is this way. And our assumption is that whenever you see a proof, some message that came from the prover, the only way the prover could have came with this message was if it did what we want the prover to do, or we think the prover should do. So again, and the difference is that on this side, which is the one I'm discussing here, we assume nothing about the prover. We only work with the actual transcript. We look into that. So somehow here the assumptions sort of look into the heart and soul of the prover and make assumptions about them. I want to point out that looking into algorithms and computer programs and saying anything about them is a big no-no in computer science, because in a very strong mathematical sense, it's impossible to say anything meaningful about a computer program in the most general setting. So, and here, basically, in soundness analysis, we say we are not trying to do this thing that is impossible and look into the heart of the prover. We are only working with this fraction of good transcripts, and which is something we actually do have access to. And now, it's not to say that on this side you don't require cryptography. You actually do require cryptographic assumptions, typically for getting a commitment scheme, Merkle trees and things like that. But that's the only part you need. So it's much leaner cryptography. It's much sort of older, and a lot of stuff is based on it. But whereas here, typically a lot of the assumptions are a bit newer, and they're sort of crafted to the particular new protocols that people come up with. So I just wanted to mention this sort of difference between soundness analysis and security analysis and some of the other ZKPs out there. Once again, I'll take some questions, and then in the next half of the talk, I want to just dive in and give you, first of all, a toy example of how soundness analysis might look like, and then make it slightly a bit more, formal to the point. Okay. So I'll just wait a few seconds to see if there's any question. By the way, just to make sure, can you hear me and see the screen and everything? Just someone can like type just to make sure. Okay, good. Great. So I see there are no questions right now. I'm going back, and I'll just continue. Okay. So now I want to sort of relate to this teaser that I placed in the when I sent an email, and I sort of said, the PCP theorem, the real name of the PCP theorem, the PCP acronym stands for probabilistically checkable proofs. But a very long time ago, I gave this informal talk, and I called it the parrot checking phone bill theorem. I won't give a theorem, but I want to describe a very simple toy construction that isn't even actually correct, but I want to use it as an illustration for how soundness analysis would work. So we have this parrot, right? It's a look. Let me show you. Here's a parrot. Let's say it has a beak. It has a bird-like body. Well, okay. So this is a parrot. So a parrot has a small brain, but it has a big mouth. Not in this picture, but right. So it talks a lot, and this parrot has a it got a cell phone like all of us, and it has this very simple phone plan, right? So the phone bill plan that it has, so phone bill, because it's a simple creature, it was offered this very simple system where 1 second of talk equals, should cost 1 cent. Good. Now this creature speaks a lot, so it makes about, makes 100 calls a day, but it can only do one addition or one summation of, one summation per day, because it has a small brain. So it gets this bill, right? This bill has, like, 3,000 lines in it. And then there's the total sum, or the total number of seconds. And then the bird is a bit worried that maybe it's being cheated. So recently the phone company noticed that a lot of parrots are dropping and moving to some other company that has a fixed plan and blah, blah, blah. So the phone company comes and says, so the company comes to the bird and says, I'll give you the bill in any format you want. Just name it in any format you want. So the question is, can we find a format that would allow the bird to check the correctness of this bill that has 3,000 lines in it, even though it can only do like one summation, one exercise of summing up, two numbers and comparing them to a third one a day. So can we do something like this? And the answer is, yeah, here's a format that the actually bird, or the owl, because the owl is smarter than the parrot. So maybe the owl has read some, theoretical computer science. So the owl comes up and tells the parrot, this is the format you want. So you want this sort of, you have this bill with like the 3,000 lines, right? So that's the 3,000 lines. And then what the parrot asks is, make it just a little bit longer and have here like all subsets. So all subsets of 3,000 of these 3,000 items, you want them, so let me explain again. For each line here, there's a subset. There's a small number. There are like 2 to the 3,000 lines in this extension. It's pretty large. I mean, considering that the number of atoms in the universe is less than 2 to the 200, this is it's a pretty long bill. Takes up a few galaxies or whatnot, even more than that, or a few universes. But let's we're talking abstractly here. So for each row here, there is a subset S of the rows, and what we have here is the sum, or the partial sum, of rows in S. So, like for instance, if my S equals 1, 3, and 5, I'm supposed to see the sum of the first 3 items. Sorry, not the first 3 items, of rows 1, 3, and 5. So this is the format that the parrot asks for. Now, why is this good? Because here's a sort of a test that the parrot can do each day. So the test is pick a random subset, and then maybe two subsets of it. So two subsets of it, S0, such that S0 union, partition it randomly into two subsets, S0 and S1. And then, so the check is, if, the row of S0 plus what's written in the row that corresponds to S1 equals the row of S. So this is sort of a consistency test. Now, what's nice about this test is that it only is a single summation of two numbers and comparing them to the third. And the idea in this encoding and adding all of these rows is that we have a lot of redundancy. What do I mean? If we look at the total sum, so for any subset, for any row here, if this is the row T, there's some other row here, which is T complement, and the sum of T complement, right? It should be that if we look at the row T and we add it up to the row of T complement, this should equal the total. So the nice thing is that the total amount is spread out very nicely among all of these rows. For each T, there's one other T bar, right? The complement of T, all the others. So like if we're looking at this S, the complement of it is the row that has all numbers between 1 and 3,000, but for 1, 3, and 5. So we can take those two rows, sum them up, and compare them to the total. And similarly, if we look at any input item, we could, just check whether it is also spread out among many, many of these rows, because, the ith row, if we look at any set, T here, so either T union I, now should also have an additional amount that is written here, or T minus I, depending on whether I belongs to T. So the process is to have the parrot each day. There are 30 days in a month. The process is for the first 29 days, the parrot does this kind of check, right? So each day it's just one sum, randomly selected. And then on the very last day, basically, so this is, so on the last day, the parrot will just check, we'll pick some T and T bar and check that it equals the sum, as we explained above, the total, which is what it needs to pay. So this is the protocol, and what are the transcripts here? So for each possible selection of a, for each random coin toss, it will specify, some S and then S0 and S1, and we'll look at this triple and see whether it's good, right? So that's like a single test. And then there's this other kind of test, which looks at two different sets, T and T bar, and checks whether they are good. So let's just go back to this process here and see what this assumption, this soundness assumption, what does it mean in this case? It says, well, let's suppose that we have an epsilon fraction of good things. Now, what is this epsilon fraction of good things? It means that we have an epsilon fraction, let's say 10%. 10% of the triples, S0, S1, if you look and sum them up, they equal S. 10%. You don't know which ones they are. And also 10% of the sets T and T bar, if you sum them up, they actually give you the total. Let's say that for each I, even 10% of the, checking of whether the ith row out of the 3,000 is incorporated correctly also is okay. So we have this sort of 10% of a huge number of transcripts, huge. It's 2 to the 3,000 basically squared, because so it's like something like 2 to the 6,000 or so different choices of transcripts and checks. and 10% of them is good. So 10% of this amount is a huge amount. Going back to, I think it was Yakov's question, is there enough information to reconstruct? Hell yes, there's a ton of information here, but it's very arbitrary and not quite structured, right? We don't know what this 10% is. We don't know that these sets, what their nature is. We just know that there's 10% of these tests that is good. So the task for the soundness analysis mathematician is to say that no matter what 10% of these tests passes, it must be the case that the phone bill is actually valid and honest, meaning that the phone company actually summed up all 3,000 items, and that's what it put in the total. Okay, so that's just sort of an intuitive explanation of what it means to prove soundness. So let me go back and ask if there are questions. I'll just wait a few, a couple of minutes to see if there are questions. And I see Aline is saying that I have, I think, Aline, you're the very first to say that I have good drawing skills. And I think, the peak and that's probably my best drawing ever. That's as good as it gets. Okay, any questions about what we did so far? Okay, so what I'll do is I'll continue a little bit more, and then I'll just return just in case there is another question that I missed here. Because what happens is that while I'm looking at the board, I can't see your questions or comments. So we would like to prove a theorem that says that if 10% of these tests that look at 3 different rows and then sum up 2 of them and compare them to the third, if 10% of the tests pass, then actually it must be the case that the that the 3,000 that these that this part is actually good and the total sum is correct. But the truth is that I do not know to prove this statement, and it may actually be incorrect. But what I described here, the protocol, is actually not very far off from what from something that we do know how to prove, and in fact, it is probably the first precursor to all of this area of proof checking and so on. And this is a beautiful result that I now want to sort of just describe very informally. It is known as the Bloom-Lubian-Rubenfeld test. And the way I want to explain it is that I want you to imagine now that for some crazy reason, suppose let's do everything that we did with the parrot, just mod 2. Just bear with me here. So what does it mean? It means that let's suppose that each each row I. So we have like the bill, the original bill itself is actually a string of length 0, 1 to the n. I mean, we picked n to be 3,000, but we could just generalize it. So this was the original bill, and we can think of it as a message. And then, so each line was just a single bit. And what we care about is we would like to sort of know what, the summation of, let's call it bi. So I goes from 1 to n. What is this thing but mod 2? So everything is done, right? The total sum is computed modulo 2. So it's just a bit, it's the XOR of all of these bits. And once again, this is, too much. This is, 3,000 bits. Doing this summation would be very hard. We're still in the parrot model. The parrot doesn't have 3,000 days in a month to do this addition. So what do we do about it? What we do is we ask for, again, for each subset, but we ask for the sum of the subset mod 2. So what would it look like? I just want to give you an example. Suppose that our suppose that our input is like, is not 3000 but length 3. So we would like to take the subset that is, we're going to multiply it. I'm going to write it using a matrix and a vector. So I'm going to write here what it equals. So if I do the subset that corresponds to the 0 to the empty set, I get a 0 here. And then I'm going to multiply it by, I'm basically writing down here all possible subsets. There are 8 of them. And now if I look at this, right, so this I think of it as a vector. And this I think of it as a matrix, but I'm doing everything modulo 2, or for those of you familiar with finite fields, I'm working in the field, the smallest finite field of size 2. Everything addition and multiplication modulo 2. So this now becomes a 1, this becomes 0, because basically the subset I'm looking at is the middle bit, and it's 0. This becomes a 1. This is a 1 once again, because I'm looking at the subset that is this guy. This is a 0. This is, I think, a 1 once again, and this is a 0. So these are all the subsets, right? This is the, so here's a row, here's some row S, and this is the corresponding subset of it. So it's basically, it's the summation of all I that belongs to S, or all I's for which the vector S is 1. And we're summing up bi. And in this case, we summed up 2 1s, so modulo 2 is 0. Good. So the phone bill that we would get would be this thing that has length. So we took 3 bits and we encoded it into 8 bits. And in general, we send, so our encoding, it's called the Hadamard Encoding. It has a name. It sends, it sends n bits by 2 to the n bits. And now the test that I was suggesting that we do has an even nicer analog. So suppose we take 2 sets here, this is S0 and S1. And we look at we look at S0 symmetric difference S1. In this case, it would be the set, right? So the symmetric difference of this row and this row is actually, right, this row. This is the symmetric difference. So it is 0, 1, 0. So the 3 entries we're looking at should be the entries this one, and this one, and this one. And we ask basically the test, the new test. This is called, so here's the Bloom. So Manuel Blum, the famous Manuel Blum, Turing Award recipient, and 2 of his students at the time, Mike Luby and Ronit Rubenfeld. This is from a paper in 1982, so it's even before the work on zero knowledge proofs came out. They have this test that they suggested to do. So you pick a random S0 and S1 subsets, and you accept if and only if the entry. So let's call this thing. It's a code word. We applied a code word, so we call this thing. This is code word W. So we accept if and only if W at the entry that corresponds to S0. If you look at its XOR with W at the point S1, if it actually equals W at the symmetric difference of S0 and S1. So this is a test that they suggested that we do in order to check whether this is what the verifier should do or the parrot should do on this version of the phone bill. And so notice that this is a test that makes only 3 queries and reads 3 entries. 2 of them are completely random. It's even better than the test that we said before because we can pick any S0 and any S1 and we can have its symmetric difference. The symmetric difference just means that basically you take and you XOR this vector and this vector. And it's not hard to see that if the phone company, what it did was took the bill and actually multiplied it, correctly computed for each entry here, the subset that is the correct one, then, let me just write this because this is often called completeness. So completeness says, and it's usually the easier part, so completeness. Oops. Completeness says if W actually equals the matrix that we put there, times the phone bill, then the probability that the test that we described accepts equals 1. And this is not too hard to show. So this is the probability over choice of S0 and S1. For any choice of S0 and S1, if you do the test that we, this test, this is the test, right? But the soundness is the amazing part. And it says, if the probability that the test accepts, probability is again over S0 and S1, probability that the test accepts W, if this probability is greater than, let's say 0.75, then actually W is something like then there exists a code word meaning something of the form, W prime that actually equals M times some B prime, such that W agrees with W prime on at least 75% of its entries, meaning that W is up to some noise, which you can, in this setting, very easily sort of discard and correct and find what the, you could correct back to the original W prime that is really encoded there. Up to some noise, the object that you were testing in which you queried only a very small number of locations, this object has amazing good global properties, and it is a valid encoding or close to a valid encoding up to some minimal noise. And once you have that, you can sort of get back W prime, and W prime is actually, you can get from it a good witness, and you can do a whole lot of good stuff with it. So again, what happens here is, so this is, probably one of the very first examples of a soundness analysis theorem, and this is, I can't overestimate the importance of the BLR test, of the Bloom-Luby-Rubenfeld test, and its impact on computer science. And again, it was a precursor to things like the PCP theorem and a lot of stuff that happened in interactive proofs and in other areas such as property testing and all kinds of aspects of error correcting codes that are extremely important in proof systems. There's several beautiful proofs of this statement. As I said, I don't want to use these lectures to do any proof. I just want to say that if you look for the BLR, if you look for this Bloom-Rubenfeld linearity test, you'll find, first of all, the original paper, and you'll find a lot of lecture notes that very elegantly explain, give some of these proofs. But what really happens here is, and I want to go back to that picture, is that we assume that we have access to an object, right? That object is the set of transcripts. And in this case, the simple case, it's the set of all triples and all relevant triples, where you pick two rows or two entries completely at random, and then the third one is dictated by them by this sort of symmetric difference operation. And you know that there is an epsilon fraction that is good. In the way I described it, this epsilon fraction was actually pretty large. It was 75%, right, of this universe. And from the fact that there are 75% of the objects that are good, you can sort of glue together and reconstruct and decode an object that is perfectly good. And that's a major step in constructing proof systems, and succinct ones as well. So I'm going to go back and ask if there are questions about this part now. Any questions about this kind of soundness analysis? So meanwhile, I'll let, I see there's one question, I'll answer it in a minute. I just want to tell you that, so for the next talk, so first of all, I think I'll start to space the talks at once every 2 weeks. So the last talk was 2 weeks ago. I'll do another one in another 2 weeks. And the question I have, and I'll put this in a poll, is whether you would like the next talk to be, so I can go either a little bit deeper into soundness analysis and describe a deep dive on the Fry protocol, which is a very important part of Stark's. So we can just have one talk dedicated to Fry. This would sort of be diving a little bit deeper. Again, I won't prove theorems, but it will be a little bit more mathy. Or if you would want to have something even a little bit higher level, which is, let's say, what does zero knowledge intuitively mean? Again, not the formal, just like I'm doing here. I'm not proving theorems. I'm not making too many definitions. It's sort of the gist of it. So like the poll that we'll construct and ask is whether you want the next talk to be sort of a deep dive into Fry, how it works, and why it works. This is a topic that I touched upon, but very informally, as part of a bigger topic of FFTs and the relation between FFTs and PCPs. But I can just have a talk about Fry. Or the other question is whether we want to do a something that talks a little bit more about what does zero knowledge mean? How can proof be zero knowledge and what it means? And I just want to emphasize, if I give this talk, you won't have Waldo appearing there, and there'll be no caves. That's not how I like to explain it. So I'll write this poll in a minute. Yeah. Okay, so there's the poll already appears, and you could answer it. Meanwhile, and you can add also a different topic if you want. Okay. Now, so let me go back and answer questions, and then there's basically one more topic that I would like to discuss in this talk, sort of just to give a tour of what other objects do people apply soundness analysis to. How does code distance relate to soundness? This is a really terrific question. So when we, okay, how does code distance relate to soundness? When we do soundness analysis on an object like a purported code word, as was the case in this example that I used. So I'll go back and then I'll continue with this very last topic of just surveying other kinds of codes and stuff that appears there. and then I'll go back and answer questions. So when the object we're analyzing is something that is supposed to come from a code word, and this is almost always the case. If the test, one way for a test to pass with less than perfect, probability, is if you just take something that is completely perfect, like a perfect code word, and just mess it up a little bit. So the best we can hope for is, since this is always a possibility, we can never hope to say that if the test passes with epsilon probability, then the object we're looking at is actually a perfectly good code word. That's impossible to reach this conclusion. But it's also not important to reach that conclusion. It's sufficient to reach the conclusion that the object we are looking at is like this W that we have here in the Soundness Theorem. It is sufficiently close to a perfectly good object. So that's what this Soundness Theorem says. It says that if the probability that the test accepts is large enough, then the object we were examining and accessing is sufficiently close to something that is perfectly in the code and has all the beautiful and marvelous properties that we would accept in this case, or expect in this case, from a code word of the Hadamard code. And the Hadamard code has amazing properties that I won't describe now. So typical soundness tests, and this is now the last topic that I want to discuss, and then I'll answer some questions. So the typical soundness tests, they, let me just pick one last color. So typical soundness statements they look at codes, at error correcting codes. And some codes are things like, we mentioned Hadamard. That was, the very first and simplest code. People look at Reed Solomon. People look at multivariate codes like Reed Muller. People look at algebraic geometry codes. People look at tensors of codes, and many, many other objects. And say something like this: if local, so they devise some local test, and they say if the probability of the local test passing, so if this probability is greater than epsilon, and this is known as the soundness error, then the object is at most delta far in some distance measure from a perfect object. Or let's say in the case of that we gave above, this was the Hadamard code. And usually delta far means, so need to change at most delta fraction of entries to correct it. So the fraction of errors in the object is at most delta. So there are two important parameters here, and those are the soundness error, that's one of them, and the other one is called the proximity parameter. It's this delta. And basically what you would like to say is that you would like to make epsilon as small as possible, and you would like to make delta as wait, no, I got myself confused. We definitely want to make epsilon as small as possible. Yeah, and we want to be able to make epsilon as small as possible for the largest possible delta that we can still do meaningful stuff with. But most of the soundness tests that are out there, and there are actually quite a few of them, there are beautiful ones. There are beautiful ones with respect to Reed Solomon and Reed Muller and the Hadamard code, which is the one that we described above, and for many others. The topic is often known as, just for those looking for pointers, and maybe I'll send an email just that gives a few pointers to this area. The names, if you're looking for more to read, these objects are known as locally testable codes. It's a huge topic in LTCs. And there are other things related to it, things like locally decodable codes. Or LDCs. And it's also connected to this huge topic in theoretical computer science called property testing. That was inspired and originated from these kinds of tests that sort of all look at this epistemological problem of, if you have some object and you're conducting a very small number of tests on it, what can you learn about its global structure? How do you know that it has good global structure? And property testing looks at objects that are not even error correcting codes, things like graphs and other combinatorial structures out there. So all of these topics have in them a lot of soundness analysis, and soundness always has the same structure, which is what I hope I got across. It is this task of local epistemology, of assuming that some small fraction of good things happens, and each one of these good things is like a single point. So it's like epistemological pointillism, but in a mathematical sense. So you have this small fraction of good things that are happening, and from it you have to work really, really hard in order to reconstruct a global object that has some nice global properties. That's the issue of soundness analysis. But so. Any questions? I see someone's just asked. So right now there are no questions. So I'll wait a few minutes. I see there's someone. So Karen wrote in the, I guess you all see this. Could you do something on the intersection of information theory and ZKPs? You've mentioned it in a few talks. Not sure if there's more here, but would be interesting to hear. Yes, there's I mean, the stuff I wanted to talk about when I wanted to talk about zero knowledge was exactly to address this. I mean, there's this basic paradox of, right, we discussed today the transcript, right? A prover and a verifier are interacting. So from the point of view of information theory, there is communication, and communication necessarily conveys some notion of information with it, or something like knowledge. So there's definitely information passing in the sense of Shannon's information theory, meaning that the verifier, as it is interacting with the prover, and more information is coming over, the entropy, or the entropy that the verifier has about what the prover might do goes down because it's getting more information. So what does it even mean to say that a proof conveys zero knowledge? What is that space about which no entropy has decreased and no information has passed? So that's essentially the topic. So I think in the poll, if I'm looking at it, more people were interested first to go into a deep dive into Fry. I'll be very happy at a later point to also address this thing, Karen. So definitely, there's a lot to say, and it's very interesting to understand intuitively. There are also different kinds of zero knowledge, ones that are a little bit more information theoretic, others that are slightly less. So we'll definitely attend to that. Okay, so any more questions on the topic of soundness? Robert is asking, is there a reason that you are using error correcting codes in PCP? Is that the most efficient way? Is there any scheme which doesn't include the error correcting codes? Terrific question, Robert. So the reason, I'll answer these in sequence. So is there a reason you are using error correcting codes in PCPs? Yes, what an error correcting code does is it amplifies the effect and sort of spreads around information about even individual bits. So to see this in the most extreme example, think of even the error correcting code such as Hadamard error correcting code that we just described today, but also Reed Solomon or any other code that you're familiar with, you can see this. So if you take, if it's a linear code, and almost all codes that people are familiar with are linear, which means that you take your information, your message, you think of it as a vector, and you multiply it by some matrix. So if you start with a 0 vector, and you multiply it by a matrix, you know what you'll get. You'll get the 0 vector, which means that the encoding of the 0 vector is all zeros. And then in any good error correcting code, if you flip even a single bit, even if you flip a single bit and you throw, you apply this new vector that is just different by a single bit, you throw it into your encoding scheme, what you get is something that will have a huge fraction of its entries being non-zero. In the case of Hadamard code, half of its entries will be non-zero. So this is a very good method for sort of taking information and converting it into sort of spreading it around. And in the context of PCPs and all proof systems I'm aware of, this is the method by which you ensure that if even a single error somewhere in the computation has occurred, that information about that error will be sort of globally spread out along the whole universe in this huge object. And we always sample these objects at random locations. So the whole way that these proof systems work is to encode not just information about the computation, but also about the validity of the constraints that specify the computation, so that if even a single constraint was not satisfied, you'll see this when you sample a random location. Now, the second question, is this the most efficient way? Yeah, today it is the most efficient way. If you go to any setting of parameters for which we know of a most efficient PCP, or even a most efficient proof system, you will find error correcting codes there everywhere. Be it if you're looking at the proving time, it will be something like Stark and Fry, and it uses Reed Solomon codes. If you look at things like proof length, it will be algebraic geometry codes. I don't know of any setting. If you're looking at things like soundness and minimal number of interactions, again, it will be error correcting codes there as well. If you look at things like you want constant query complexity, again, you'll have error correcting codes everywhere. Now, is there any scheme which doesn't include the error correcting codes? So if you're looking at information theoretic proof systems, the transparent ones, the ones that include Ligero, Zikaboo, Aurora, Fractal, Stark, I'm not aware of anyone, and they somehow require the error correcting codes in order to spread the information. The other flavor of ZKPs, the ones that use cryptographic assumptions and sort of say, oh, the prover is, the only way the prover could have sent the message is to do this kind of computation. So there you still have error correcting codes or polynomials, but they're used more implicitly. Because, for instance, take one example, in a snark, you could think of it as, in the pre-processing phase, someone is sampling a single entry from a Reed Solomon code word and sort of giving you all the information to evaluate your various code words at that single entry. But you could also take the view that there is no error correcting code used there. There are polynomials, but you're not explicitly, encoding stuff and sending it or committing to it. So I hope that answers the question. Any other questions? Okay, so I want to thank you, everyone, again. In 2 weeks' time, we'll see which day of the week. We'll see what our constraints. We'll hold another one, and the topic will be, according to the poll, it will be just a deep dive into deep fry. Again, there'll be no. I promise you, there'll be no. Well, we might mention a theorem, but I won't. Prove anything. I just want to sort of give a more fluffy explanation of what's going on there. And then we'll take it from there. So thank you very much, everyone. And I'll stay around like a couple of minutes just to see if there are any other questions or if there's something in the chat, whatever it's called. Yeah, the chat on the side. Okay, so I'll end the broadcast, but I'll stay around to answer questions. Bye, guys.